Hey guys, welcome! Today we're going to do some Scilab activities together, as well as tell you guys what I have learned in the course Modeling and Simulation. So let's get started. So first, we're going to create a 5x5 matrix named ModSim using random integers of up to 100. So that would be rand of 5x5 times 100, and let's wrap this using uint8. Okay, since this is just 1 to 100, so I think uint8 is fine. So let's check our modsim matrix. So there. Next, we test if elements of modsim have less than 60. So to do that, we're going to use the less than operator. So there. It's just a Boolean matrix. Okay, false if this is false, and true if this is true for an element. So next, we find for the elements of each column, or rather, find for the elements on each column that are less than 60, and extract the elements per column. So to do that, we're going to use the find function. So let's say index underscore lt60 is equal to find modsim less than 60. So find returns the indices where modsim elements are less than 60. So for example, this one is true, right? So element 1, 3 is true. So yeah, it's 9. So 9 is less than 60. So those kinds of values that are less than 60. And it will return, this find function will return the indices of such. So this is 1, 2, 3, 4, 5, and so on. So there, let's check our index underscore lt60 vector. So there. Then next, extract the elements per column. To extract the elements per column, first we're going to need the length of index underscore lt60. That's just 13. Okay. Next, we're going to extract, so we're going to need the loop. Let's say for I is equal to 1 up to n, so that's 1 to 13. Then let's create a new variable, modsim underscore lt60 of I. Don't forget this notation, or else you will have a 1 by 1 matrix. We need all. So is equal to modsim of index underscore lt60 of I. So there. End. So this is your index, right? Because this holds the indices, and we put it as an index of modsim. So there. Let's check for our modsim underscore lt60 vector. So there. This contains the elements where it's less than 60. They are definitely less than 60. So this is good. Next, test if elements of modsim have greater than 28. So we just do the same. So mod sim, instead of less than, we use the greater than symbol. 28, mod sim less than 28, greater than 28 rather. So there, Boolean matrix. True if it's true, false if it's false. Okay. Find for the elements on which column that are greater than 28. So again, we're going to use the find function. Extract the elements per column. So we're going to use for loop again. So find for the elements. So we're going to get the indices using the find function. Let's say index underscore gt28 is equal to find mod sim greater than 28. So this will return the indices of the elements where they are greater than 28. So there, let's check for our index underscore gt28. So there, we have 18 elements. Let's store this, or rather the length of this vector in n, length of index underscore gt28, or let's say, let's use O. Okay. O is equal to length of index underscore gt28. Okay, let's check for O. 18. Good. Let's use a for loop again. For I is equal to 1 up to O. So 1 to 18. Mod sim underscore gt28 of I is equal to mod sim of index underscore gt28 of I. So let's end that loop and let's see the output. This mod sim underscore gt28. Okay. So there. These are the elements that are greater than 28 in mod sim 5x5 matrix. So there. We're done with our Scilab activity. Okay, so what did I learn in the class modeling and simulation? So modeling and simulation is present now in our modern world. So your flight simulators, your games, online games, they are basically products of models and simulations. So what is modeling and simulation? So modeling and simulation is a problem-based discipline. It allows for repeated testing of a hypothesis. It's cheaper and safer than real-world experiments because usually this is done using computers. They are much cheaper than your big materials to actually construct systems. So it also helps to validate research. So there are time-advanced approaches in modeling and simulation. You have your time-driven simulation and event-driven simulation. So time-driven simulation, it's widely used for simulation of natural systems. It advances time with a fixed increment. So increments of delta t time units. State variables are updated for each time interval. It's precise but inefficient since it has to change state variables at a given time. Then you have your event-driven simulation. So this is mostly used for queuing and optimization problems. Periods of inactivity can be skipped. It's more efficient since inactivity can be skipped, so state variables can just be updated when an event occurs. So it jumps clock from event time to the next one. So as I said earlier, state changes occur at event times. Next is discrete versus continuous modeling. So you have your continuous modeling, discrete modeling, and hybrid modeling. So for continuous modeling, this is usually done using analog means such as measuring voltages. Discrete means is digital, therefore it's represented in numbers. And hybrid modeling is a combination of the two, continuous and discrete, using analog to digital converters and digital to analog converters. Modeling and simulation are based on finite state machines. Finite state machines are machines that can be at one state at a time. It's used to design computer programs and sequential logic circuits. Changes state through a transition function. Hybrid dynamical system. Finite state machine plus a collection of dynamics models. So this is a simple hybrid dynamical system model. What is computer simulation? Computer simulation, it models behavior of a real or imagined system over time, used to analyze the behavior of systems. Parallel and distributed simulation. These are simulations that execute on multiple computers or multiple processors and network computers. So the benefits of parallel and distributed simulation are reduced execution time because you have so much computers. Tasks of the simulation can be distributed to large amounts of processors and computers. Distributed simulation can be geographically distributed through networking means. Different types of simulators can be integrated. And of course, since you have so much processing power and computing power, it can be fault tolerant. If one fails, another can take over. Simulation can be applied to analytic simulations for analysis purposes. Virtual environments, so distributed virtual environments, first appeared in or applied in military applications. Your wargaming simulations, FPS first-person shooting games, training environments, test and evaluation, entertainment applications, social interactions and business collaborations, for education and training as well, telecommunication networks, digital logic circuits and computer systems, and transportation simulation. So, parallel versus distributed, what are the differences? Parallel computers are in close physical proximity, so usually in a cabinet. Usually, parallel computers are homogeneous machines, so they come from a single manufacturer. Parallel computers also has low latency because they're in close proximity. So an example of parallel computer is computers with symmetric multiprocessing. So this is a computer with many processors. Also, non-uniform memory access, which is access of memory of a different processor. SIMD machines, single instruction multiple data machines, and usually variables or state variables are shared in parallel computers. While distributed computers, on the other hand, these are network computers. Distributed computers can be geographically distributed. Distributed computers can be heterogeneous machines, so they can be different kinds of machines. And usually variables are not shared, and usually communication among distributed computers are done through message passing, through network means. Distributed virtual environments are sufficiently realistic representation of a system. Participants embedded in the environment. They are geographically distributed, so through distributed computing means. And synchronization requirements are usually relaxed, and there is distributed interactive simulation that is used in building distributed virtual environments. It enables interoperability among simulators. It defines an infrastructure for linking simulators, for building realistic, complex virtual worlds. Networking and data distribution. This is usually applicable to distributed computing simulations. So there are message passing services. So there is reliable delivery, where a service guarantees that each message will be received at a specified destination. Message ordering, it guarantees that successive messages arrive in order or sent in order. So you also have your connection-oriented versus connection-less communication, and unicast and group communication, the DIS and NPSnet as examples of unicast and group communication. An overview of networking technologies was also discussed, such as the types of networks, local area networks, wide area networks, metropolitan area networks, topologies such as bus and ring topologies, networking requirements as well, such as low latency, reliable delivery, group communication, quality of service. Communication protocols were also discussed because this is necessary for the communication of distributed computers. So your TCP/IP, OSI layer model, asynchronous transfer mode for different types of medium, group communication, broadcast and multicast. So broadcast is sending message to all systems, while multicast deliver messages to a multicast group. And finally, data distribution methods were discussed. Data distribution aims to provide efficient, convenient services to ensure that each simulator receives all of the messages that is relevant. That's what I learned in the class Modeling and Simulation. Thank you very much for watching, and bye for now.